In this lesson, we're going to learn about functions and the basics of functions, some terminology to go along with functions, and how to recognize if a data set, table, or graph is a function. So let's begin by defining a function. A function is a relation in which there's exactly one output for every input. For example, or in other words, for every x in your data set, there is exactly one y that goes with it. So let's say that in your data set you have an x value of 2. As long as your y that goes with 2 is always the same output, so let's say you have a 2 for x and your y is 7. Even if 2 were to come up again in your data set, another 2 comes up, as long as it's still an output of 7 in my example here, then your function then your data is a function. Okay, it's working properly. So I like to think of functions as a machine where every time something goes into the machine, it should always produce that same output. The same product should come out. So let's say we're creating socks and we have a sock machine. If I put in blue thread to my sock machine, let's think of the blue thread as our X value. Then every time our machine works with blue thread going in, we should produce a blue sock. If that occurs time and time again correctly like that, then we have a machine that's working, and that machine would represent a function. Now let's imagine that one of those times I put blue thread in, however, I get a green sock out. There is an example of a machine that's not working properly. We had an X value produce two different Y's. Therefore, that is not a function. That is not a machine working properly. You can think of this in terms of expressions or functions, equations. So let's say I made up an equation like 2x plus 1 equals y. To determine if this would be a function, I would choose different values for x, and we'll do this later. But just to show you, I would put a value in for x, and as long as every time I put that same value in for x, I'm always producing the same y, then my equation would be a function. So let's say I put a 2 in for x. When I solve that, 2 times 2 plus 1 should give a 5. As long as every time I put 2 in for x in this equation, it always gives 5, and there's no other possible value for y that we could find, then that equation is a function. So let's say I now chose 1 to put in for x. This time, if x was 1, my input's 1. So now I'm changing like the color of the thread in my sock machine. Now I'm putting purple thread in, right? If I put purple thread in, I should get a purple sock out. So let's confirm that that happens here. If I put 1 in, I should get 2 times 1 plus 1 is 3. As long as every time I put 1 now into that function, I'm getting a 3, then yes, it is a function. Okay, so let's look at an example. This is a way of representing data, which is a map. And so if I'm looking at this, this implies that in this data set I have a value or an x value of 1 that produces an output of 6 or a y of 6. I have an x value of 1 that produces an output or y of 7. And I have an x value of 2 that produces a y of 7. So in this example, we are determining whether or not this data would represent a function. So your x's are your inputs, and your y's are your outputs. And remember, for our function, or for this to actually be a function, we need a properly working machine, where every time the certain value goes in, it always produces the exact same value out. So we can see that we put a 1 into this machine. And one of the times the 1 came out and produced a 6. However, the second time we put the 1 in, it produces a 7. So because the input of 1 does not have exactly one y, it has two y's, this is unfortunately not an example of a function. And I can't quite erase, but this reads, this is not a function because the number 1 has two different outputs or answers. Even though the 2 works properly, the input of 2 always gives an output of 7 over and over and over again. it still has an error when the input is 1, so the whole thing would not qualify as a function. Here's a second example. Here in this set of data, we have an input of 1 producing 6, and then we have an input of 2 producing 6. This time you'll see the outputs repeat, and that's okay. It's okay if your output ends up being the same. What matters is that at every time 1 goes in, it produces the same value out. So you can see no matter how many times I put 1 in for x, I always point to the output of 6. I never point to something else. I'm always getting a 6 when 1 goes in. And when 2 goes in, I consistently always get 6 every time. So my machine is working properly. I'm always producing the same output every single time. So this is a function because the number 1 and the number 2 have only one answer when they go in. Even if that answer is the same, that qualifies as a function. So we'll often look, when we're looking at a set of data in a map or table, we'll see if the x's repeat. If the x's repeat and have different y's, that will indicate that we do not have a function. If the x's never repeat, then we have a function. All right, so deciding whether an equation is a function. To do this, and I showed you a basic example, what we'll do is create a table of ordered pairs by plugging in several x's of your choosing and solving for y. So let's say we have the equation y equals the absolute value of x. What we're going to do is set up a table, and we will choose some x's. And I always recommend choosing some negative x's. Oh my goodness, this thing is writing all over the place. Some 0, and then some positive x's. And when I do this, I'm now going to take each input and put it in the place of x in the equation and see if I consistently produce the same output. So when we put negative 2 in for x, we are getting y equals the absolute value of negative 2. And when we simplify that equation, the absolute value of negative 2 is positive 2. We get a positive 2 for y. And ask yourself, is there any other possible value you could get as an output when putting x of negative 2 in? And in this case, we will always get positive 2 for y. So that tells us right there is no other possible output that could be associated with an input of negative 2, so it's working with negative 2. Now we do the same thing with negative 1. So the absolute value of negative 1 is positive 1, and it will always be positive 1. If we put 0 in for x, we're going to get an output of 0 for y. If 1 goes in for x, we get an output of 1 for y. And if 2 goes in for x, we get an output of 2 for y. So you will notice that we don't have any x value repeating or producing 2 different y values. So because none of the x's repeat with different y's, we have a function. Next, let's look at this example. So it looks similar, however, we've got the variables flipped. Here we have x equals the absolute value of y, and we'll set up our table where we pick some x's and figure out the y's. Now it's a little bit trickier with the absolute value around the y, so we're going to do these one at a time. If I were to choose and use negative 2 as my x value, to figure out what its output would be or what the possible y is, we have to ask ourselves if there is a y, or what that y's would give an x value or output of negative 2 in this sense. So with negative 2, there actually is no value for y that could give us the absolute value to be a negative. So there's actually no solution for x being negative 2. And that's okay as long as there's consistently no solution for that value. So let's try something else. Let's say we tried x to be positive 2 instead. Let's ask ourselves what y value would simplify in this equation for a positive 2x value. And so if I took the absolute value of positive 2, then that would be 2. And that works. However, absolute value could also be a negative number. If I took the absolute value of negative 2, do you agree that it would still be positive 2? Hopefully, yes. So here I have x of negative 2 again. However, it also works with y of negative 2. So right here you can see the same x going in, but different y's coming out. I could do this with 1. If I think about putting 1 into this function. And again, we have to do this one a little bit backwards to really see that we're not producing a function. But if 1 goes in for x, there are 2 possible values that y could be that would still produce a positive 1 in this equation. So again, we have an example of 2 different y's, same x. So this is going to prove that we do not have a function. Here I have an input of 2 giving negative 2, and then later an input of 2 now gives positive 2, so our function is not working properly. Again, if your x's repeat with different y's, that is an indicator of your equation not being a function. Okay, when we're looking at graphs of functions, we can use what's called the vertical line test to determine if our function, if our graph is a function. So to test for a function by the graph, if any vertical line passes through one and only one point of the graph, then it is a function. If you have a vertical line hit your graph more than once, that is going to be an example of an x value producing multiple different outputs, therefore not creating a function. We'll look at that. So here's our first graph. In red, we have the this function graphed, or I shouldn't have said function yet, we haven't determined that it is. So we have a graph. And we are going to determine if this is function by using the vertical line test. So what we'll do is we'll drop a vertical line down this graph and see if that vertical line would intersect this graph in more than one place. It hits right here, and that's the only place it would hit. Now visualize dropping this vertical line multiple times throughout this graph. As long as everywhere you would drop it, it only hits once, and you never would drop it and have it hit the line more than once, then this is a function. So because the vertical line test passes, it only hits the graph in one point, anywhere you put it, then we have a function. Here's our next example. If we drop a vertical line here, I can see it intersects in only one spot, and I could drop that vertical line anywhere along this graph, and it's only going to intersect at one spot. So this horizontal line right here is another example of a function. Let's look at our third example. Here is a graph of a circle, and when you get into higher math, you'll learn how to write equations for circles in your that can be graphed. Here, if I drop a vertical line, let's say I drop it here on the edge. This is called what's a tangent line, just a little extra knowledge for you. But if you drop that line right on the edge, there is a way that that line would only intersect your circle at exactly one point. However, if we drop the line somewhere inside, it's going to hit that circle more than once, in this case 2 times. Therefore, this line is not passing the vertical line test, meaning it's hitting the graph more than once vertically. So this is an example of our function, of our graph not being a function. I want you to imagine that these are 2 different points, and let's say the x value of this point is 3 and the y value is -1, and let's pretend this one has an x of 3 and maybe a y of 5. So right here is the example of why this data set would not produce a function. We have an x, or an input, repeating and producing different outputs. So our machine is broken, it's not a function. This doesn't mean that your equation would be wrong or that it couldn't be graphed at all. Certainly we can see the graph. It's just that that is not a graph of a function in particular. I have a couple practice sites that will just present us with some different scenarios to determine if these graphs are functions. So let's take a look at a couple together. So here's the first example, and we're determining if this graph, the blue that's graph there, is a function. So if I were to drop a vertical line here, oh, it's not letting me drop it. If I drop the vertical line here, it would intersect at one point there. However, if I drop the vertical line here, you can see it would intersect at 1, 2, 3 different points. So that right there is not a function because there is a place where the vertical line test fails. Here's our next example. And let me see. I was going to try to pull up the pen. No. Okay. Anyways, here's our next example. If I drop a vertical line anywhere here, you can see it's only ever going to hit the graph at one point. So this one would be an example of a function. Okay, this example, or this graph, and you take the graph in its entirety. So these two pieces do make up one graph. So while I could drop a vertical line here, and it would only intersect in that one spot, if I were to drop it here, I'm hitting this graph in 1, 2 places. Therefore, this is not a function. Let's look at one more. Okay, in this one, if I'm dropping my vertical line, it would hit once there. If I drop it around here, it hits once, 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 and so on. Actually, there's one more I wanted us to look at. So anyways, that last one was a function. So here's our last example. I want us to do one more of these. So in this graph, I've got these open circles. And if you remember from inequalities, an open circle means it does not include that point in the graph. So if I were to drop a vertical line at x equals 2 here, you can see that it does go through right here and right here. However, because this is an open circle right at that point, we are not including that point in this graph. So this vertical line only intersects the graph once right there because the circle does not include it. So this actually is a function because everywhere we drop the vertical line, it would only intersect at one point that's included on the graph. Here's a quick example. I lied. One more. That is not a function. Here, if I drop my vertical line, you can see my vertical line is intersecting infinite times all along here. So here's a point, here's a point, here's a point, here's a point, right? There's tons of x values with different y's, so that is not a function. Okay, that was our first one. Let's quickly look at a couple more examples of function graphs. This one is one made with data sets. So let's get some points. Okay, so this has dropped some data points on the graph for us, and we need to determine if this data set would produce a function. So if I'm dropping vertical lines through these points, would I ever hit more than one point? No, I would not. So this example is a function. Let's get another set of points. Here, if I drop a vertical line through my graph, right here I'm hitting 2 times. My vertical line's hitting 2 times, so I'm not passing the vertical line test, therefore this is not a function. And you can see that when x is 5, it produces an output of 7, but the next time we put 5 in, it produces an output of 15, so this is not a function. Okay, and with that, we are going to move on with our lesson. So let's do a little bit more practice together. Actually, I'm going to ask you to determine if these 4 would be functions or not. So let's pause this video, decide if these 4 would be a function or would not be, and then we'll come back together and check. Okay, so you should have gone through all 4. And in this first one, you can see that 0 goes in, produces 5 out. Ask yourself, every time 0 goes in, does it always produce 5 out? It does. Okay, what about when 1 goes in? 1 always produces 5, so that's consistent. 2 always produces 5. 3 always produces 5. My x values never produce different outputs, so that is a function. Number 2, I have x going in, Think of your thread going into the sock machine and producing a -1 out. Then that same X goes into the machine, but now it produces a 0 out. Right there, we have two different outputs for one input, therefore not a function. For number 3, if I drop the vertical line down, I can see there is a place where that vertical line would intersect more than once, in fact, 3 times to that graph. So it's not passing the vertical line test, not a function. And number 4, I have -2 going in. One time it produces 3, the next time it produces 4. I have one input with 2 different outputs, not exactly one output, so not a function. Even though the 1 works, or -1 works, and the 0 works, because the -2 has multiple outputs, that will not produce a function. Okay, couple last things before we finish up here. Just to review some vocabulary, remember that the domain is the set of all X values, or all your inputs in a set of data. So if you were asked to state the domain of your set of data, you would list all of your X values. This is your independent variable. And your range, or your set of all your Y values, depends on your X values. So when you're looking at a graph, if like X goes in as 5, the output, that Y value, depends on what happened to the 5 in your equation to maybe produce 12 as the output. So the Y depends on your X. So for example, if we were listing the domain for this data set, it is made up of the X values 1, 2, and 5, and we would list it in curly brackets separated by commas. To list the range, that would be all of your Y values, 3, 4, and 5, and again list it in curly brackets. If you had a domain, well, I'll not get ahead of myself. Okay, last thing, if you are in class, we are going to do a hand squeeze activity where I'll have 3 students start out in a line holding hands, and I will tell them to start, and the person on one end will squeeze the next person's hand, and once that person feels the squeeze, they pass it on to the person next to them, and we time it to see how long it takes. So what I'm going to do is give you the data set for one of my classes. And so that way you can have a set of data to be able to do your hand squeeze activity, even if it's not going to match the data set from class. So in one of my classes, we did the hand squeeze, and these were the times we got as we added people onto our line and made that longer and longer. You can see the time increased as we went. For the most part, they did get faster at the end. Okay, so here's your data set for the hand squeeze activity. So if you need that, go ahead and copy that, pause, and copy that onto your hand squeeze paper. And you are now practicing, so you're filling it into this hand squeeze assignment and putting that data in, and using this document to now practice what we just learned about functions and reviewed about domain and range. So you will graph your data. Remember, we just reviewed domain being the independent variable and your X values, and range being your dependent variable and your Y values. So you'll start by graphing all of these points. And the number of students is your independent variable, because we could decide that. We could affect how many students were standing up in line. The time depended on how many students were there. You could see by that data set that the more students we had, for the most part, the longer it took for us to have everyone's hand get squeezed and passed down the line. So make sure to label your graph, your X values, your inputs, number of students down here, and your time up here, and just space it out so that it's nice and clean and spread out. Then you're going to answer some questions with vocabulary based on the hand squeeze assignment or activity that we do in class. So go ahead and use the remainder of this time to fill out your hand squeeze assignment. And that's it for functions today.